world you are. My name is Gus Nathan. I'm the Research Director of the HILT CRC. I'm very pleased to welcome you all to this very exciting forum addressed technology pathways for green iron and low carbon steelmaking, a webinar, and you'll see we have 4 companies who will give 4 time slots, but within that we have got 6 presenters. So we have Dr. Gerald Wimmer from Primetals, Dr. Gerhard Terblanche from Metix, Dr. Markus Dorndorf from Tenova, Andrea Esthuizen from Tenova also, Dr. Alessandro Del Rocco also from Tenova, and Simon Nitschke from Hatch. So it's a very experienced group here, and of course within the HILT CRC, one of the key features of our CRC is we seek to engage technology providers as well as producers, as well as researchers, as well as government stakeholders from across the sector. So today we've got a very experienced group of technology developers who bring their industry perspective onto this exciting challenge. Next slide, please, Adam. So we'd like to begin by acknowledgement of country. This is our traditional owners of the land. There are people from all around Australia, different traditional owners, but the Kaurna people are those in the Adelaide Plains where I'm situated and where the HILT CRC main offices are, and we offer our respect to their spiritual relationships with country and custodians to the Kaurna of the Adelaide region, their cultural heritage, which is still important to the Kaurna people today, and of course the land has not been ceded. Thank you, Adam. Next slide. So the agenda today, the way the webinar will run is I'm going to introduce the various the speakers one at a time for their sessions. First of all, there'll be Primetals. Each of our companies have 15 minutes. If they finish before the 15 minutes is over, then there is some time for questions for their particular presentation. We'll go through them one at a time, and then at the end we have approximately 20 minutes for a more wider panel discussion. So feel free to put your questions into the Q&A box. You'll see in the screen there's a Q&A button, so please type them. It's great if you can also note which of the presenters you'd like to present or which of the companies you're addressing the question to. That would also be helpful. Of course, the webinar is also recorded to allow those who don't get a chance to see it in person to also see it later. So our speakers are all happy with that, and I hope everybody who's listening is also happy with that. Next slide, please, Adam. So first of all, Dr. Gerald Wimmer from Primetals, and you see that he's a very experienced presenter. We're great to have him here. He leads their work. He's the, first of all I should say, he's the Vice President of steelmaking, and he leads their work on green steelmaking, smelted technology. His expertise in development, implementation and optimization of these processes throughout this field. He's previously held positions of Head of Technology. He holds a PhD in mechanical engineering and a master's in business administration. So please, Gerard, thank you, and over to you.
Thank you for the nice introduction. So I'm allowed to start this session. I'll share my presentation with you. So just give me a short sign if it's okay, and you can see it in full screen mode in a minute.
Thank you.
As I'm starting this one, I would like to start a bit with a broader picture of why we are doing all this one. So we are changing our industry. We are going green. So this will not be a small step. This will be a big step. That's why we call it a transition. So we have the green transition upcoming. You might remember that some 5, 6, 7 years ago, we had digitalization and industrialization. Some people are wondering what's with this topic. Was it completely washed away by the wave of green projects we are doing? We do think it's not the case. So we will have both. We will have greener industry and a more digital industry. That's why we'll call this the twin transition. And that's what I would like to present to you in the next 15 minutes. But to start with, and to start all the session, I think it's worth to go a bit deeper and have a quick look on the overall picture of our industry. why we are doing this. And the reason you can see on this slide here, on the very first line, we see the typical way how steel is made today. So today, globally, 70% of steel is made via the so-called integrated route, using material preparation step like coking plant and sinter plant, and then the blast furnace to transform the iron ore. And here, of course, Australian iron ore is playing a major role into hot metal, which we then refine into the converter to crude steel. We need a lot of energy for this one. And in this route, almost all the energy we need is coming from carbon. So we feed the blast furnace with a lot of carbon on the one hand for reduction, on the other hand for heating. We collect the off-gas and convert the off-gas into electricity that is powering the plant. So we hardly need any external electricity in such an integrated plant in a modern one. But a lot of carbon, with the consequence that we have a very high CO2 output of almost 2 tons of CO2 per ton of steel. So we always call it the iron and steel industry, and I'm always joking when you look on this number here. A typical integrated steel plant is producing twice as much CO2 as it is producing steel. So when it comes to output, one would have to call it a CO2 plant and not an iron and steel plant. But, and this is also very important, what we see in the second line, steel itself is a very green material, because steel can be very nicely recycled. There's a lot going on about scrap quality, scrap upcycling at the moment. So of course, scrap has its challenges, but when we do it properly, we can recycle steel again and again and again without any quality losses. And in this recycling route, of course, today done to 99% using modern electric arc furnace. Primetals here has, for example, this quantum furnace, which is even more energy efficient thanks to scrap preheating. We come down with the energy to 300 kilowatts per ton and to a very, very small carbon input that we need. It's never carbon free. So if somebody is talking about carbon free steel making, I have my doubts, because we need the electrodes, we have the metallurgy to be done. But this amount of carbon is that low that we already see first plants like SDI in the United States. They managed to get all their carbon input for the process, not yet for the electrode, but for the process, from biochar. And this is then resulting in very low CO2 emissions of just 90 kilograms per ton, which, if it's coming from biochar, can be carbon neutral. So first point, yes, the way we do today to 70% is not compatible with our climate target. Second measure, steel itself is a very green material that we will need in future. So shifting to other materials, not using steel, but using plastic or aluminum instead, is not the solution, because steel is very sustainable and good to recycling. So finally, we'll come to the conclusion that still we have to make steel out of iron ore, because scrap is not enough available. So we already do recycling, but even in the developed countries, we need to make some steel out of iron ore to feed them demand. And in the growing economies and the developing countries, that's even more the case. And that's why for low emission steel making using iron ores, direct reduction seems to be the promising solution. So instead of using a blast furnace fed by carbon, we use a direct reduction technology. Most dominant today are shaft technologies. Colleagues from Tenova will present their technology. Metix is an alternative, another technology, both using pellets. So we use a pelletizing plants going into the shaft, and here we use either natural gas, already common today since decades, or in future to use hydrogen. And then we get DI, which is highly metallized but not molten, so we need an electric arc furnace to melt and get crude steel. And in this route, if we use hydrogen, we hardly need any carbon, but we need a lot of electricity. And where we see where the electricity is going, most of the electricity is required to produce the hydrogen that we need for the reduction work. And when we compare now to the first line, we see, yes, green steel making with low CO2 emissions, even on iron ore base, is possible. So we can reduce the CO2 emissions by almost 90%, but this requires a completely different energy input. Instead of carbon, we need electrical power. Sounds easy on the first step, or instead of buying carbon, just buy electricity. But when you think about logistics, carbon, coal, coke is very easy to be transported, very easy to be stored. And even in this geopolitical different times as we have today, it's quite easy to make a forecast. And when you expect rising prices for coal, just buy it for 1 year, 2 years, 3 years, quite easy. For electricity, that's not the case. In the amount we are using it here, 4,000 kilowatt hours per ton, Maybe you have an electric car or a battery at home. If you compare this to typical battery technology, we are far off that we could store this energy. So we need it 24 hours a day, 7 days a week, continuously supplied. And we need it there where the production is happening, where we have the hydrogen produced and the direct reduction is happening. That's why transport is also becoming a topic when it comes to electricity. It's not that easy as for coal, and that might be smarter to shift the iron making where the electricity is available instead the other way around. So it seems pretty clear. We use as much scrap as possible, and the rest we do via direct reduction using common shaft technology feeding electric arc furnace. Yeah, it's not that easy. If we have a quick look into the raw material side, here's a typical diagram. Primetals is using this since quite some time, so you might already know it. So we see here the global produced iron ores, transported ones, 1,500 million tons a year, an incredible amount. And you see on the vertical axis the iron content in blue and the gangue content in yellow. And of course, the gangue in the classical route using electric arc furnace is becoming slag. So the higher the gangue content, the higher the slag amount. And we see the very good iron ores here on the right with very small gangue result in reasonably low slag amount in electric arc furnace, so the electric arc furnace can handle. Nobody's happy about too much slag because slag in electric arc furnace is reducing the yield, it costs energy, but as long as this amount is low, we can live with and we can use it. These low-grade iron ores and these medium-grade iron ores would result in very high slag amounts, 600 kilograms per ton. So the slag pot on such a furnace would be bigger than the steel ladle. And that's why these medium to low grade iron ores today are used in a blast furnace and they do not fit to the electric arc furnace. And that's also explaining why this topic is so important for Australia, because most of the Australian iron ores are somewhere here. So today they fit very well to the blast furnace. They struggle to fit to common electric arc furnace. That's why we have these new technologies under development where we use a furnace for low grade iron ores, but not an electric arc furnace, but a new type of furnace. Primetals is calling it smelter. Others are calling it electric smelting furnace, ESF, or OSBF, open slag blast furnace. All fine for me. Let's see if we can agree on a name in future. The only name we do not like to hear is submerged arc furnace, because with this highly metallized DI, it's not possible to submerge the arc. You will create a shortcut and delete the arc. And with this very simple furnace where no metallurgy is done, we run on low basicity. We can also process this mid-grade to low-grade iron ores with a much lower slag amount. So slag amount stays reasonably low. And as this process in this furnace is very simple, we just do melting and final reduction. This slag is very comparable to blast furnace slag. So the slag still can be used in the cement industry and we do not get the problem at landfilling. So that's why the future green transition will not only include the classical route already known today and very successfully used in a lot of plants. Primetals is doing just one of these plants in Germany for Dillingen, Metix shaft technology and modern electric arc furnace. We will also need technologies that allow to use low-grade iron ores, which is the majority of iron ores available today. And this requires this new type of furnace, which is simple furnace just doing melting and reduction. No metallurgical refining work, and all the refining work we do in a dedicated aggregates, the BUF converter, and this also explains why this route with these two steps, smelter plus BUF converter, is very interesting for plants already having a BUF converter in operation, and especially plants having very large heat size that is not that easy to transfer to electric arc furnace, like for example POSCO, ThyssenKrupp or the Japanese plants. And of course, there is further development. Why to do pelletizing? This is again energy and CO2 emissions. Is there also a solution to do direct reduction without pelletizing? And here, this new fluidized bed technology developed by Primetals Technology HIFO is under development. A different way to show this green transition summarized here. So on the very left, we see the classical route where we have the material preparation. Then the blast furnace is very busy guy. In the blast furnace, we do the reduction and the melting and then refining in the converter. While in this very new route, we eliminate the preparation step. We directly go to fluidized bed with the sinter feed without preparing it. And then we split. Instead of having one electric arc furnace that is doing melting, final reduction and refining, we split into two steps. So we have this new furnace, which is called smelter for melting and final reduction. And we get metal high in carbon, which we feed then into the BOF converter for refining, so a two-step process in the steelmaking. That's the future process we think for Australian iron ores will play quite an important role. And that's then our prediction. How is Primetals seeing the future? So this is our prediction, how the technologies will shift. So 2050, what's to see there? Blast furnaces are still there. So we have a very big fleet of blast furnaces, and even if all our green ambitions work out well, this will be also only a gradual transformation and not an abrupt one. So also in 2050, we still see quite a significant share of steelmaking made by the blast furnace and the BOF converter. That's why we think optimizing of this existing route still pays off, because there is still several decades where these processes are in operation, and if you can reduce the CO2 emissions, you can directly save CO2 emissions. We see the scrap-based electric arc furnace share rising. Why not more? Because there is not more scrap available. All the scrap that's available is used. Scrap collection is already on a very high pace, so there is small room for further increase, but not that much. That's why not more than 1/3 of steel can be made out of 100% scrap, and the rest will be based on DI, where we have this classical route using high-grade DI going to electric arc furnace and the other ones going to the smelter, plus some new technologies which are on the horizon. For example, electrolysis, high temperature, low temperature electrolysis, but here it's not yet proven to which scale this technology will ramp up. Quick outlook how Primetals is developing. So we have 4 processes under development. Let's start with the HI4, where we combine direct reduction step using this new fluidized bed, where we use ultrafine material as an input. So very fine material with a grain size of less than 50 micrometers. Several reactors, material is reduced, and then we either compact it, hot compact iron, or we directly feed these fine materials into the smelter, and from the smelter we get metal high in carbon. That's why we call it hot metal or iron, and a slag which is granulated and sent to the cement guys. And for this combination of HI4 direct reduction per smelter, we started a project called HI4 Smelt, which is financed by Primetals, First Alpine, the steel plant next to my office here, and Rio Tinto. So why is Australian mining company investing in a demonstration plant just to prove Primetals Technologies processes? Because this will show that Rio Tinto's Australian mid-grade iron ores can be processed in such a route in a green way to produce green steel. Quick overview on the process sheet. So first step, of course, is material preparation.
1 minute, please.
Preheating, and then we go to the smelter. The smelter is already known to the industry now. Just a quick representation how this looks. So it's a big furnace having a bath in which is continuous in, and we continuously operate and tap it like a blast furnace. And this is now the realization. We had the groundbreaking last year. In wintertime, we prepared the land, and now the civil works is under execution. And we're now raising the building up, and first columns are going to be placed this week. I mentioned digitalization. So it's not only green, it's also getting digital. Why? Because in all these plants where we have this new route, process in the first step is getting more complex. So we have a new process route in parallel to your old one, which is an advantage if you can use it well. If you cannot control the process well, then it's just a nightmare and a chaos. And second reason is, when we do a new plant, a digital plant is less costly than an old plant with a lot of hardwired control boxes and control panels around. And that's why digitalization in the new plants automatically plays a role. One of the topics I like most is this mobile information support systems, where you have mobile devices.
Gerald, and we just need to draw it to a close soon, please.
Yes, just coming to an end, where we have all this information then on the tablets available for documentation. And we will start up this HI4 Smelt plant next year in August, and hopefully in the next seminar I can then present first results. Thank you.
Great. Well, thank you, Gerard. That was very exciting to see the progress, and I think you did a great job also in introducing the scene as well as putting your technology in the context of that. So thank you very much. So now we hand over to SMS Group, where Gerhard is going to give us perspective from Metix. He's a business development manager who started his career at Xstrata Alloys in 2001. You see he's had expertise in ferrochrome production-related activities, pre-oxidation and process understanding, extensive experience in AC/DC furnace operation, been in Metix since 2023, and he also is graduated from South Africa in chemical engineering. And you'll see there were lots of applause from everyone there for the first presentation. So thanks again, Gerard, for that. And now we look forward to Gerhard to share your screen, please. Thank you.
Fantastic. Thank you. I believe you can all see what I'm sharing.
Yes, good. Thank you.
Great. Okay, so thank you for the introduction. And obviously, you can see our title that we have on the screen, Navigating the Shift to Low-Grade Iron Ore, and then the market reality as well as the technology pathways. And it fits quite nicely with the webinar title, to understand the pathways to green iron and low-carbon steelmaking. And as we go through the presentation, there'll be some references similar to what Dr. Wimmer has presented, but I will just reiterate those figures when we get to them. And obviously to understand what these pathways are and how Metix as part of the SMS group can realize these pathways and this decarbonization of the industry. Good. So, I mean, as we all know, decarbonization is not only about energy, it's also about raw material quality, which is the challenge for most companies. However, we do see it as an opportunity. Not all ores are suitable for low carbon routes, as we know, especially the DR-EAF routes. There's an increasing reliance on high-grade ores or upgraded materials, especially with the EAFs that's recently being built and commissioned. And the industry is busy shifting from energy only to energy and feedstock optimization. And it's clear to understand how Metix and the SMS group fits into this, but we'll get to that a bit later. So what is the present situation? We all know that the steel industry is volume driven. I mean, it has been like that since the beginning of the steel making process, and it's volume driven with flexible feedstocks. And mostly it was be dominated by the BF-BOF route with a wide tolerance for different ores. The value chain was built on scale and logistics efficiency, and there was limited historical constraints on ore and also on ore quality. However, we've seen that there's significant change in that. And if we go to what the future holds for us, so if you're considering what we've said, what the present situation is, and we need to understand what the future holds to design and supply the right equipment to fill this gap and also the right technology to fulfill these processes. So the transition to energy and emission constrained systems from where we were as a present, the growing role of hydrogen and electricity, as was also mentioned by the previous speaker in terms of the electricity, the preference for high-grade ores and scrap, although the availability are getting less, and we'll also see that on a graph similar to what we presented earlier. And also there's the regionalization of steel production. So it's important to understand that you cannot just have one technology for all regions. It depends on what happens in that region, and it depends on what the requirement is for that specific region and that specific client. So the impact of transformation. I already discussed the shift to an emission-driven production model, which means low carbon or decarbonization. Obviously, this brings increasing OpEx and complexity. I mean, you do understand that the margins in steel making and iron making is not as favorable as it is in other commodities. So OpEx plays a very important role. And then processing moves forward toward an energy abundant regions. Obviously there where there's energy, where there's electricity, where there's low cost, that's where the electricity and that's where the process fits in perfectly. And obviously then there's a disruption of traditional value chain. and change, and as we've discussed earlier, under the present situation. So again, considering all of this, you need to understand what technology to apply in what region to decarbonize efficiently, but still looking at the right OPEX as well as the right CAPEX. And again, as we go forward, you'll see where the SMS group and Metix fits perfectly into understanding the regions as well as what technology to apply where. So in terms of global trade flows and the quality shift, as you can see from this graph, iron ore supply is highly concentrated from Australia and Brazil, while the demand is dominated by China. And I mean, that we've seen so many times. High-grade supply remains constrained despite the growing demand that you can see on the graph on the right. And that was also indicated by the previous speaker. And market is not volume constrained, but quality constrained. And there's a structural gap emerging. And that gap we need to understand, and that's the gap that we need to fill with new technologies and new pathways. Now, interesting enough, total production does grow modestly in terms of ore, but high-grade demand grows faster. DR pellet supply remains structurally limited, and that's a big bottleneck for the DR EAF routes. And there's a clear mismatch between decarbonization demand and feedstock availability. And again, keep that in mind when we start looking at what technology to apply and how to apply it. And the nice thing about Metix and the SMS group is that our technologies are bypassing pellet dependence, especially looking at fines processing and different smelting routes, which we'll also get to a bit later. So, low-grade ores dominate, and we do know that. And 80% of the global iron ore is low-grade and still growing in absolute terms. Low-grade exports are declining, which means that we need in-situ upgrading of this material at the source. And decarbonization depends on unlocking low-grade ores economically. And unlocking a low-grade ore means that it must be economically viable, it must be efficient, and it needs to give you the same product and the same results as what we've seen from the blast furnace as well as the DR grade EAF route. Good. So what do we have? So within Metix and the SMS group, there are different routes, as also has been discussed by the previous speaker. So these three routes is the scrap EAF, the blast furnace BOF, and then the pellet-based materials, which we know can be high grade or low grade. So what the Metix as part of the SMS group did is we have differentiated and offering across different routes. We have the OBF or open bath furnace, and yes, as previous speaker indicated, there's different names for this. However, we do refer to it as an open bath smelting or an open bath furnace, OBF. And this OBF, it's a reducing furnace, which do use electricity, but from this furnace, we can produce the exact same hot metal and slag, which comes from a blast furnace, which means it fits seamlessly into the current processes to replace the blast furnace. Secondly, in terms of fines, because we know there's a lot of low-grade fines available, and not to pelletize, and again, looking at the OPEX, we can easily put that into our Circomet process, which I'll discuss now, which is part of the SMS Group's technology, which has, it's trademarked as Circo Red, the previous Metso technology which we have acquired. And you can seamlessly integrate that into our open bath furnace. And then our process integration optimization means that we can fit it seamlessly into greenfields as well as brownfields. Now, this is an important slide. Why do I say that? Because every region has a different drive. It's important that Metix and the SMS Group as technology suppliers understand what to do in what region. So there's no global optimum. For Europe, it's cost and policy driven, as we know. For the Middle East, it's energy driven with a lot of DRI growth. China, India, we all know that the BOF still remains dominant. And then the energy and ore dictate competitiveness. So from the SMS Group and Metix side, we have successfully de-risked each region to understand what technology to apply where. And again, within the group, we've also developed PAT, which is a plant assessment tool, which can assist you very quickly to make a decision in terms of OPEX of where to build what technology. So future landscape. I mean, this was also presented quite clear by the previous presenters. I'm not going to go into detail in that. We understand the shift towards EAF-DR routes, but again, constrained feedstock quality and scrap availability. Low-grade ores must be leveraged, and Metix has successfully developed our open bath furnace to utilize low-grade ores, and then also in a fine format, coming from a pre-reduction unit, which is the Circo Red. And then also the additional value from bypassing agglomeration, which is CapEx and OPEX intensive. So we have a strong alignment to actually fit this growth with our Circo Red fines-based DRI product, our smelting to produce a similar blast furnace products, and then end-to-end flow sheet optimization, which we also have available. Then also just to add our easy melt, which has been developed by our colleagues from Paul Worth, which makes the blast furnaces green, which is also included into this graph as a significant growth, which will come as part of our decarbonization drive. Good. So not to waste any more time, because I think I only have about 4 minutes left. What's quite key for the SMS and the Metix technology and how we differentiate is our Circo Red product, which is hydrogen-based. And the nice thing about our technology is that it has been de-risked, the process up to TRL7 on our smelting capacity. We've done significant test work already. Our pilot scale work has been completed. Our equipment is sitting on TRL9. On the Circo Med, which is a hydrogen-based fine pre-reduction units, there are also references which you can go and look up. There's a reference plant which has been built in Trinidad. So the product that we have is the Circo Med, where we have a one-stage fluorized bed reactor combined with our smelting furnace. And again, it's a bespoke and tailored solution, which is already developed, and it will be per region and per client request. We normally don't just give one solution to everyone. So the Circo Med is available and de-risked. And then also the Circo Red, which can be a two-stage fluorized bed process, which is also part of the SMS group offering, where obviously you can feed from this, create an HBI or a DRI, which can be directly used in an EAF, which means that we can utilize high and low-grade ores and feed into an EAF or into a smelting furnace, depending on what the requirement of that specific client is. Not to waste lots of time on this slide, but specifically applicable to the Pilbara ores. The SMS group, together with Metix, has gone into a PFS with Fortescue to specifically design this Circo Med plant for the Australian ores. And then the phase 1 plant is for about a capacity of about 2 million tons per annum of green iron, which will ultimately go to about 10 million tons. And this our Circo Med, as I said earlier, it's a hydrogen-based fluorized bed coupled with our open bath furnace technology. So in conclusion, there's the market shift. It's quality, not volume, and it's a real constraint. Decarbonization requires integration of low-grade ores, clean energy, and flexible technologies. There's no universal solution. And Metix and the SMS group, as said earlier, we design according to the region to have an optimal decarbonized solution with already de-risked equipment. And this enables us to supply technology across the whole value chain, enabling low-grade ore to green metal pathways. Good. So that's from my side. I think I am within my 15 minutes.
Thank you very much, Gerhard. Another excellent presentation, and I think between the two of you, you've now set the scene really well about the challenges and the pathways, and how the importance of the ore properties links into these various processing pathways and the way the technology developed. You see a lot of applause also coming through from that presentation from both of them, so thank you all. Just reminded everybody to please feel free to put questions in the Q&A box. And now we hand over to our third group, which is from Tenova. And I'll just briefly go through the three speakers from Tenova. First of all, Dr. Markus Dorndorf. He's the Senior Business Development Director with extensive experience across this pathway. And you'll see he did his PhD at the Helmut Schmidt University. And then we have Andre Esthuizen, who's the General Manager for Sales and Marketing, also very experienced in commercial strategy, client technologies, also very experienced with 20 years in the markets throughout this sector, who holds an engineering degree also. Then we move to our third speaker is Dr. Alejandro Del Roca, who's the Business Development Manager with a PhD from Milano, and he focuses on a range of innovative technologies, also business development. And so the speakers can say more. I won't spend more time on them, but please look at their CV details. But I'll hand over to Markus first. Thank you very much.
Thank you, Goose. Pleasure to be here. Let me share my screen. Give me a short sign when you can see it. Yeah, very good. So first of all, good afternoon down under. I'm excited to see that so many of you are here in this webinar, and I appreciate your attention. We are three speakers today, so due to the fact that my former speakers, Gerald and Gerhard, did a very good introduction into the general transformation processes, I can focus a little bit more on the technology and also on the group itself, just to introduce our Tenova group to the people who are not yet familiar with. So my name is Markus Dorndorf, and I'm representing this Tenova group here, and we consider ourselves as let me say, a technology developer and provider, especially for solutions in the decarbonization of the steel industry. Now, wait. Yes, just a brief overview. We are part of the Tekin Group. This is a privately held multinational company, and we have our group has 6 main companies that operates worldwide, and Tenova was born as a spin-off of the Tenova Group. We operate worldwide, also in the down under, especially with our TAKRAF group, so TAKRAF and Delcor. This is our global technology leader in mining, material handling, and minerals processing. For us, the sustainability isn't just a word, and you will see it in our technology portfolio. This defines completely our actions and our product portfolio finally. What does it mean? So the fields in which we are primarily active are the iron and steel industry. We have also technologies for hydrometallurgy, grinding and texturing, aluminium melters, pyrometallurgy, and also port equipment, which is also relevant in down under. Especially for the iron and steel making industry, Tenova offers a fully integrated range of technologies that supports the transformation of the integrated route towards green and sustainable, especially from the iron ore and ferroalloy ores to scrap and to secondary metallurgy and liquid steel solutions. So we have different types of electric arc furnaces in our portfolio, an iBlue concept my colleague will later refer on, and also post-processing solutions for ladle furnace and vacuum degassing technology. And we also have our own direct reduction technology I will show you in a minute. And as said, also our port equipment and bulk material handling is part of our expertise. So how metals are made, I think all of you know about that. So we have the ores, which we need pelletized in order to use it in our direct reduction technology, but we have under the big umbrella pyrometallurgy, of course, also solution to deal with all iron units available, so especially with scrap, pig iron, and DRI, which we can produce by ourselves. And another part of that is also from waste hydrometallurgy, where we can create concentrates, mineral ores, or also battery recycling, what we call black mass. Where in the steel value chain, Tenova can contribute to mitigate the carbon footprint, and that's why we are so active in the decarbonization of the steel industry worldwide. So we have, with our direct reduction technology, directly the solution in hand to do CCU and CCS, but the main approach is to avoid the CO2 emissions, so that we call it CDA, carbon direct avoidance. We have also a lot of technologies in waste heat recovery and injection systems. All of them are hydrogen ready, so we are already prepared for the far future when hydrogen will be available to a great extent. This is what already Gerald and Gerhard presented. We are on a big way of transforming the steel industry, so we electrify the steel industry. Gerald made a very clear explanation on that, and we have explicitly our portfolio designed to support this electrification of the steelmaking process. These are the main steelmaking routes where we can support you and our customers. We start with the ANAC iron process jointly developed by Tenova and Danieli. This is just an overview of this cycle process. It's hydrogen ready, so we can easily switch between 100% natural gas and 100% hydrogen as reducing gas, and also use other reducing gases. And we have the feature in this cycle process that we have CO2 sink. So that means we take out the CO2 and in a very pure gas composition, and we can use it, for example, in the beverage industry to have a CCU approach. That's why we have also been chosen as by NeoSmelt. And here the main goal of this pilot plant, we call it semi-industrial plant for NeoSmelt, is to test especially the Pilbara ores. Currently we are running a series of back tests in Mexico where the HIL mother company sits. And with these back tests with some pellets containing Pilbara ores, we would like to better understand their behavior. And also recently, Rio Tinto has published that they executed some industrial tests in the zero reformer plant in Baowu, and they are also getting good results. So this is our contribution already with our DR technology in Australia. So here are some of the reference plants from this technology. As said, we have a wide range of melting technologies and aggregates, and I would like, before I hand over to my colleague Andre, to explain you a little bit more about the electric arc furnaces. Also here we have various solutions and concepts for melting various iron-based materials and converting them into steel. So within a basic top charge electric arc furnace, but our main driver in this transformation process, also from the productivity point of view, is our ConSteel solution. So this is a continuously feeded melting furnace or electric arc furnace, which is capable to produce up to 400 tons of liquid steel per hour. So we can, with that furnace, let me say, go easily into the integrated steelmaking plants in order to say, look, we can have the production capacity you have run before with your blast furnace technology, and we can keep up with the electrified solution, so we can provide electric arc furnaces with productivities of above 2.5 million ton a year. So this is a very specific technology we have developed over the last decades. But also other furnace concepts. We have, for example, the flexible modular furnace, which is a hybrid solution acting as converter and also as electric arc furnace between. As said at the beginning, we are a technology provider, so we only focus, or we mainly focus on the technologies that makes this sustainability approach alive and brings us forward. So we are very strong in technology as no man on the floor, in hydrogen ready burner technologies, and we have also our own electric charging or input concept with the direct feed developed together with GE. Yeah. This brings us a lot of advantages, especially here in Europe, where we are the main driver for this big transformation process of the integrated route. And also here, it shows the world our references that this Consteel solution is the perfect match for the transition towards a green steel industry in the future. But as my colleagues before also said, a key aspect is and will be the digitalization, data analysis, and also the usage of artificial intelligence to make our facilities and processes even more efficient and transparent to our customers. And we are very active and strong here. And all this together results into, let me say, the main, all the playing fields we are in. And so we have a lot of experience, especially from Europe, Northern and Americas, where we drive this green transition. And now I would like to hand over to my colleague Andre, who will give you a more detailed approach to our smelting technology. Thank you very much.
Thank you. Let me know if you guys can see. Okay, I saw some nods. I think I have to start off saying that for the audience that's listening, there is Tenova, Primetals, Hatch, SMS participating together on this webinar. And I like to refer to us as frenemies because we are extreme competitors, but at the same time, we all have this common goal we are working towards. High tide raises all ships, so we all get along very well. Now, Dr. Wimmer, Gerhard has explained so much on the long-term primary focus on the challenges that the industry is facing. I just wanted to take a short left turn, looking at the timelines that my colleagues have shown, where we're talking about 10, 15, 20 years into the future to really turn this industry around. There's also a need for what I call complementary technologies that we need to focus on. And just the 2 points, or two of the technologies that I wanted to raise today is slag treatment and HBI or DRI preheating. Marcus has explained the experience that we have with the direct reduction technology. Electric arc furnaces is shooting up all over the world. Open slag bath furnaces, it is, as an engineer, it's probably the coolest thing I've worked in my 20 years as a pyrometallurgist, but it is so damn complex and expensive. And when we're talking about a market where profit margins are measured in cents per ton sometimes, we really need to tread carefully on how much the new technologies that we develop costs. So as a complementary technology to the EAR, electric arc furnace stream that has been shared previously, we've developed a slag treatment solution, smaller scale, that stands on its own, with the intent of retaking what we call black slag from the EAF furnace and converting it so that it is similar to blast furnace slag that we can sell as an aggregate into the cement industry. Because as the blast furnaces trend down, the cement industry will have an increased need for aggregates that the blast furnaces no longer can provide. How often do we see cement plants next to big blast furnaces all over Europe? Another technology that we've developed...
we need to draw the Tenova presentation to a close soon, please. Thank you.
Okay, cool. And then I just want to say that, again, we know that HBI is an important, or HBI hub, especially in the Middle East. We know that the HBI produced in the Middle East, because it's the best place to produce HBI in the world at the moment, allows us an opportunity to add a complementary technology to the electric arc furnaces so that we can improve the performance of an electric arc furnace. If we preheat the HBI, for every 100 degrees we do so, you get a 20 kilowatt hours per ton saving on the performance of the EAF. And now, Alessandro, you have seconds. Sorry.
Thanks. Let me finish this overview, giving you also an idea of what's coming up next. So we talked about upstream liquid steel production. Now it's also a good idea to look into downstream, so which means essentially hot rolling of semi-finished products. To this respect, Tenova has also developed a portfolio of downstream decarbonization technologies, namely for reheating and heat treatment processes. And this portfolio is mainly organized into three largest areas. The first one is related to efficiency improvement. So essentially having regenerative combustion as well as high temperature air preheating, possibly also high temperature fuel preheating in the case of very lean fuel gases, such as lean blast furnace gases, may be particularly relevant. So for getting, say, the first 20% of CO2 reduction. And then in terms of further reducing total carbon footprint, there is for sure the possibility of looking into green hydrogen combustion. So we have developed a good flameless solution to that respect. And the idea is that in this case, the combustion system can be used as a totally flexible user within the hydrogen supply chain, which means no hydrogen storage needs to be provided on site. And this is, we believe this is really a huge simplification, both in terms of insurance cost as well as safety works required. And finally, we have also solution in terms of direct electrification of the heating process, which means for slab reheating, say 1250 degrees C of process temperature, then induction preheating is the sweet spot solution. So having inductive preheating of slabs at 750 degrees C, then followed by a shorter reheating furnace, mixing basically electrical energy input and fossil fuel input, which can also possibly offset by more and more hydrogen use. And finally, for lower temperature processes, such as traditionally treatment or longs product reheating, which occurs usually at 1150 degrees C, then induction as well as resistive heating are for sure the main electrification solution, which allows also 100% of process decarbonization. And with this, I think we are finished since time is gone. Thank you all for your attention.
Thank you very much for another excellent presentation from Tenova, and also highlighting the wide range of components in the steel making process, right through to the energy making systems and integration of fuels, etc., in combustion. So thank you very much. Another excellent presentation, and you see more applause in the chat. Just please remind everyone to add your comments and questions into the Q&A. And now we hand over to Simon Nitschke, who will give us the presentation from Hatch. And you see Simon leads a team of 300 people globally. He's the Managing Director of Technologies. Did his mechanical engineering degree at University of Adelaide, and now is based in Brisbane. So Simon, thank you very much. I'll hand over to you. Thank you.
Yeah, thanks very much, Gus. And I know a lot of people on the call today probably have experience in presenting at iron and steel conferences these days. And I know as you get later and later in the session, you can play a bit of a game of bingo with your slide deck and start dropping some of the introductory slides, thanks to my colleagues earlier on who have covered a lot of the context. So I appreciate all the good discussion so far. Look, as Gus described, I'm the Managing Director of Equipment Technologies at Hatch. We have a team of about 300 specialist engineers out of the 10,000 in Hatch worldwide that really focus on equipment and technology development. And most of those people have experience in pyrotechnology, both in ferrous and non-ferrous applications. So very suited to contributing to the discussion that's going on at the moment in the iron and steel space. Of course, like all OEMs, we like to give our technologies names. You've heard a couple of them today from some of our colleagues and competitors. We refer to our CRS Plus technology that does represent our ESF, or electric smelting furnace technology offering into iron and steel, that stands for the continuous reduced iron steelmaking process. It was a technology we originally developed back in the 2000s when we were focused on continuous steelmaking technologies. And more recently, we pivoted that towards the DRI ESF flowsheet, as that's become obvious as a beneficial flowsheet alternative in iron and steel more recently during the green transition. So that's really the technology I want to focus on today, and perhaps demystify a little bit this box that is called the ESF on so many flowsheets, and why we've got such confidence that that's ready for deployment into DRI ESF alternative flowsheets. I'll skip most of this slide, but needless to say, I think I agree with all the other presenters. It's not so much a matter of will the transition happen to DRI ESF as an alternative. It's more how quickly that may happen. And certainly our expectations align with some of the earlier presentations. Look, there are many factors that may impact this over time, but certainly we expect some portion of iron making to occur in that alternative DRI ESF flowsheet in the years ahead. And certainly from Australia's perspective, which is where I sit today, and where some of our team certainly calls home, we see that very important for obviously the Pilbara ore as an export industry, given that it represents so much of Australia's GDP. Again, the ore making challenge around, or iron making challenge around low grade ore is fundamentally about gangue rejection. We've heard a lot of information about that, so I won't go into a lot of the details on this slide. And in preference, I'll skip to how we see ESFs and how we in Hatch look at ESFs fitting into this flow sheet. So the good news is that ESFs do provide us with equipment capable of rejecting that large amount of gangue that we talked about in an efficient manner and at the volumes comparable to blast furnace operations today. And therefore, they really do represent a very credible alternative pathway in the future. So our teams have always found it useful to see DRI ESF flow sheets as simply splitting the combined pre-reduction and smelting processes that are normally all completed within the one vessel of a blast furnace into those two separate process steps, the pre-reduction in the upstream direct reduction furnace, and then the electric smelting furnace being able to complete that work and achieve the challenge of that gangue rejection that we talked about earlier. Now, our experience in designing and building some of the largest electric furnaces in the world today, we certainly recognise the importance of not only the equipment technology itself, but looking at the layout of the smelting facilities and how that integrates into a smelter that's capable of handling the capacities that do make it credible for blast furnace replacement. And so we've looked at certainly in detail a couple of different layout options. We see credible opportunities for coupling a single 2.5 million tonne per annum DRI facility upstream of 2 ESF furnaces, or alternatively for even larger capacity throughputs, perhaps 2 DRI units into 3 ESF. So and often not really respected or looked at in terms of the detail up front, but it's important to recognise that DRI ESF has the big advantage of actually being credible to replace the sort of capacities that are necessary if we are going to look at getting rid of those blast furnaces as we move forward, or certainly taking up some of the capacity that they otherwise would have produced. Now, in terms of the CRS Plus furnace itself, the fundamentals of this equipment design is not new. Hatch has been designing, developing and refining the components of stationary, high-powered, large-scale smelting furnaces in the non-ferrous industry and ferroalloys industries for more than 70 years. Many of those component-level technologies originally developed have direct applicability to iron-making ESFs, And they can benefit from all these developments in the past. And each of these features we've incorporated into the overall CRS Plus furnace design that we're now carrying forward as our offering in this space. Now, we see a lot of these component level technologies very critical to that long-term successful operation of CRS Plus at scale. And I just wanted to mention a couple of them briefly. We've heard from others about the importance of producing high-value slags, very similar to what comes out of a blast furnace. And that's certainly possible as part of ESFs. Perhaps most importantly is the combination of an active binding system that provides constant sealing on all of the refractory lining in all three dimensions and allows us to thermally cycle the furnace as necessary for maintenance activities and long campaign lives. We've got tight sealing of that upper gas space above the liquid bath, and that's important for providing a CO-rich off-gas stream and opening up the possibility and value of integrating low nitrogen steel productions out of ESFs. It's continuous operation, as we've mentioned earlier, which leads to high availability and less complexity in terms of integrating into industrial power grids, particularly weaker grids. The use of self-baking Soderberg electrodes is an important aspect. They allow for true continuous operation of these furnaces at significantly lower cost compared to graphite electrodes that most will be familiar with in EAF furnaces. ESFs also allow for the recycling of iron-bearing waste streams. They're relatively insensitive to alternative feed addition in parallel to the primary feed sources that we're providing to the furnace. And certainly powers up to 120 megawatts on a single 6-in-line furnace can pragmatically match to those modern blast furnace replacement capacities with only 2 or maybe 3 units in some cases. Those furnaces themselves at 120 megawatts, we envisage being about 400 square meters in hearth area, and they are well within the known and proven smelting power density limits that are demonstrated today in some non-ferrous applications. The size of that furnace provides very stable metallurgy and in fact also provides buffering capability to upstream and downstream operations. So at Hatch, we focused on 3 pillars of work that really ground us with the confidence that ESF technology is ready for deployment in commercial DRI ESF flowsheets in the very near future. The first is around fundamental processes being demonstrated in existing iron making or electric iron making references. So we said earlier that electric smelting is not new, and in fact, even in iron making applications, there's several industrial examples that are in operation. And while most of these relevant examples are 40 megawatts or less, it's important to recognize that we certainly have ilmenite applications operating up to 80 megawatts today. So that gives us certainly confidence that the fundamentals do actually work at scale. From an equipment technology and design perspective, we've got industrial commercial scale demonstrated in adjacent industries already at the scale that we're talking about necessary for ESFs. I mentioned in non-ferrous, we've got industrial examples which are much closer to that necessary scale at almost 100 megawatts today. And they're physically at the geometry that are required for what we see as that commercial scale CRS Plus furnace. And it's really this that gives us the confidence that the equipment technology itself is ready to support that genuine blast furnace replacement. And particularly when you start to consider that a lot of that key componentry around the long campaign life that will be necessary on ESFs is already incorporated and demonstrated on those very large non-ferrous furnaces, including the cooling elements and the active binding system. And thirdly, the third piece of the work that we're doing is really around fundamental test programs and participation in critical demonstration projects that focus on refinement and leveraging of not only the history and experience we've gained across those first 2 pillars, but also looking at the most critical specific scenarios to the challenge that we face. And one of those that we've talked about at length today is the Australian challenge around Pilbara and low-grade ores in particular. And even when a technology is proven in analogous applications, we recognize that it's only truly de-risked when we are able to show that it operates successfully in specific areas of commercial interest, such as Pilbara ores in Australia. So I'll just pause for a moment, and sometimes we get the question around the scaling of the furnace power to the levels that we need, around that 120 megawatts mark. And as I mentioned earlier, we certainly have examples of Hatch furnaces operating around the 100 megawatt mark. And it's useful to reflect on the evolution of that smelting intensity in furnace design over time. So at Hatch, we've developed larger, higher power furnaces over a sustained period of time, as you can see on this plot. And the step to 120 megawatts is easily foreseeable as far as we're concerned, using existing technology and without significant technology risk. That smelting intensity is typically compared on a kilowatt per square meter of hearth area basis for electric smelting. And otherwise, this limit is certainly within the current density of the electrodes, are capable of handling the current density needed for 120 megawatt operation. And certainly at that 400 square meter mark of physical furnace size, well within the hearth smelting intensity limits as well. So I'm certainly confident that the scale is certainly within reasonable technical risk profiles moving forward. I'll briefly pause on a list of those Hatch furnaces that provide us with that confidence around those first two pillars that we described of the fundamental process and equipment technology being ready and available at scale. And there's a couple of trends that I wanted to point out on this list as we review it. So the first is really around the iron making examples. They're certainly on the lower end of the power level as I described previously. However, they do still provide us with that confidence in the fundamentals. And that's really the part that they're playing there. And most recently, they've proven to be really important industrial examples that have allowed us to further de-risk the fundamentals as we look forward to the future in scaling ESF technology. Interestingly, as you move up the power scale to low to medium power levels, you can see a mix of circular and rectangular furnaces. Circular maxes out at about 90 megawatts for various technical reasons that we can go into in another discussion. But for those truly higher power operations that we're talking about, 6-in-line rectangular furnaces certainly offer a greater opportunity for that robust, large-scale geometries necessary to match blast furnace throughput. And finally, as we approach some of those highest power examples in ferronickel at least, our designs are already demonstrating that 100 megawatt mark and certainly provide solid operating confidence that not only those smelting densities are practical, but also in terms of the operating windows for practical considerations such as slag handling that's already well known to those non-ferrous operators and can be brought across to ESF operation very easily. So shifting to that third pillar of refinement and demonstration, there's two aspects that we're focused on here. The first is that we've established an ongoing lab scale facility supported by our team in Johannesburg. And the focus of this work is really around the development and refinement of feeding techniques using both natural gas and carbon-free DRI, and the resultant carburization of the hot metal that we're able to achieve out of that smelting process. And based on this work, we certainly believe that this fundamental testing remains critical in confirming expected carburization levels, and certainly the feeding patterns will be one of the most critical design refinements necessary during the early commercial demonstration of ESF technology at scale. Hatch hybrid feeding is a technique and arrangement that we've shown results in higher carburization of that hot metal, and we're continuing to refine this knowledge base through this fundamental test program. Finally, our third pillar is also critically supported by our involvement with projects like NeoSmelt. And you heard Tenova refer to their DRI equipment being also incorporated into NeoSmelt, and we're happy to be a part of this project as well. It's a joint venture between BHP, BlueScope, Mitsui, Rio Tinto, and Woodside to demonstrate DRI ESF using Pilbara ore. And the Hatch Crisp Plus furnace designed specifically for this project will be a 9 MVA, 7 megawatt single phase AC furnace using 2 graphite electrodes. And importantly, it's intended to be a third slice representation of what we believe the commercial Crisp Plus furnace will look like. So it's very important from a scaling perspective to have it at the size that it is. The project's currently completing feasibility and is transitioning to execution with the final investment decision expected later this year and operation in 2029. The video here shows the latest flyover of the full NeoSmelt large-scale pilot facility that has been developed by Hatch and to be built in Kwinana in Western Australia. And the facility includes material handling, including the DRI storage, the Tenova supplied DRI plant, Hatch Crisp Plus ESF. And really what we see in this project is a unique opportunity that's brought together 5 industry-leading partners along with 2 very critical OEMs, but also importantly leveraging the operating experience of BlueScope, both from their Port Kembla operations as well as their New Zealand steel operations. And it's the combination of all that that really sets NeoSmelt apart as such a critical demonstration project in this new space. It's an enormously important project for Australia. It's certainly in terms of Australia's green iron ambitions, but I would also suggest for the iron and steel industry at large. There's a lot of eyes on this, and it's important that this demonstrates that flow sheet as an early example of pathway to commercial success. So finally, just some conclusions. Certainly, we see crisp electric furnace technology as an effective equipment option for that low-grade iron ore process route in particular, and therefore its applicability to Pilbara specifically. Electric iron making technology is not new. We've got lots of examples, both historically and currently operating, where we can get some confidence in the fundamentals that are at play here. Our technology, that Crisp Plus technology, is built on many, many years of electric furnace design in adjacent industries. And we really see that technology providing an implementation-ready example of ESF equipment ready to drop into those DRI ESF flow sheets. And finally, the importance of that NeoSmelt project can't be underestimated from our perspective. It really will be one of the first opportunities to prove the performance of that alternative flow sheet at scale using Pilbara iron ore. So very excited to be part of that. And I'll leave it there. Thank you very much for your time.
Thank you, Simon, and thank you all. And it's been a really great series of presentations and seeing the technology moving forwards. More applause coming through from everybody. So just to the audience again, please feel free to add some questions into the Q&A. In the meantime, I'd like us to just obviously the ESF or electric smelter furnace, which goes by a number of names, is being identified as really a really critical platform, and that's certainly been one of the important platforms that's been identified also by our HILT CRC and all of our partners, which is why we're investing in that a lot. So maybe I'd like us just to continue some discussion across all of our speakers on that topic, maybe moving back to Primetals. I'd like us to think of, you've talked about all the importance of the ore and how the technology does have a lot of established platforms in different industries and also some in the iron and steel sector, but obviously we realise there's ore specific challenges, and that's why we need to do more testing associated with that. Maybe if you could all perhaps give us a bit more of your perspective around where you see the different testing that you're undertaking and how you see that upscaling and implementation pathway for each of your platforms, maybe with Primetals first.
Yeah, thanks for the nice question. As mentioned by Hatch, the technology for this new furnace is not completely new, so the equipment exists, also the furnace size exists. What's new is the material we are using. So up to now it was used mainly ferroalloy industry, where we had a lot of coke, a lot of reduction work and only a small amount of metal to be produced. Now this is changing. We have now low-grade iron ore, but still we have very high amount of metal and very small amount of slag coming from these processes compared to what we see already operated in the industry. To be honest, Primetals is a newcomer of this type of furnace, so we do not have references for submerged arc furnaces. So we started from scratch, and that's why we are very happy that we already have a pathway for testing and implementation implemented. So we have done our lab tests. We have a nice facility in Austria with several electric arc furnaces, which we modified a bit to run them as submerged arc furnaces and later then as ESF. And now we're doing this project together with Rio Tinto here in Linz, where we do a first smelter, 3 tons per hour, 3 megawatt of electrical power, and a diameter about 3 meters. So it's kind of 3 furnace. So this is still a small furnace. That's why this is a round one. This will feed by fines or compacted material coming from the Haifa plant and will start up next year in August. A year later, we will start up the next size of furnace, which we are now implementing together with POSCO. So there also construction work is ongoing. This is this HyREX project where we do this Phoenix direct reduction technology, transform it from coal-based to hydrogen. And of course, this Phoenix technology of coal-powered melter gasifier does not fit to a green production route. So of course, this has then also to be combined with the green smelter. And this furnace is already 30 megawatts rectangular, 23 meters in length. So it looks already like a small industrial rectangular furnace. And based on these two developments, POSCO plant will go up a year later in 28. I think we are well positioned to go for the full industrial size of, same as colleagues presented, we think for a large shaft technology, which will be the first one, we will need 2 large rectangular smelters, each of them 100, 120 megawatt. So 29, I think we are ready for the first industrial plant.
Yeah, great. Thank you. That's really interesting. And maybe from Metix, maybe if you could also talk about what you see the timeline for upscaling, particularly, of course, when we consider ores of more of the context of the Australian or the Pilbara type.
Okay. Thank you for that. So from Metix's side, and again, from our side, as I said during the presentation, that the equipment has been de-risked up to TRL 9 level. It's commercialized. We also have a range of references for this type of equipment. I think that's the first one. The second point is in terms of the Pilbara ores or low-grade ores. And you're most welcome to go and view a paper that we've published last year after the ASTEC conference. We've advanced electric smelting from pilot scale validation on our short open arc technology. And that being said, so the process for different ores has been de-risked up to TRL 7. The equipment is TRL 9. Currently, we are supplying the 200 megawatt rectangular 16-line furnaces for ThyssenKrupp to both consume the hydrogen-based DRI and natural gas DRI. So from our side is that the technology is available, the process has been de-risked, and the application to the Pilbara ores is similar. We've also done a lot of work on that ore. So from Metix's side and the broader SMS group, our technology perfectly fits what's happening in Australia, and we've proven it up onto high TRL level.
Great, thank you. And I think we've kind of heard some of this from Tenova already, but maybe you could talk a bit more broadly around some of the other challenges you see, for example, with bringing electricity to plants at that kind of scale, especially if we're going to be replacing blast furnace. How do you see the broader challenges associated with bringing in electric arc furnace technology into the sector?
Nathan, I'll answer that. We live in an industry. Sorry, I misunderstood. Go for it.
Okay. No, 100%. Thank you, Andre. I think so the way Metix sees it, and again, I want to refer back to the presentation, is that on electricity side, we do know that it's regional specific, and that's why we design also regional specific. However, in terms of electricity, if you see what is happening in Australia, specifically the Fortescue project, is the amount of renewable energy that has been installed to actually cover this shortage of electricity. And that's that's the one way we see it going forward, is there's a lot of renewables. The scale is, however, high, I do agree, but there's a lot of effort in renewables. Well, that's the one point. And then on the other point, some regions, as discussed earlier, the power supply is quite constant and much cheaper than other areas. And that's how we approach it. So from our side, we don't see it as a concern. And then also what we also do is we bring that into the design. And I think that's applicable to all the presenters today, is that within a design, and we all tested on pilot scale, as I said, we've de-risked up to TRL 7, is that you design the process that it is the most energy efficient on electrical consumption. And those three things, so focusing on renewables, focusing area specific, and then having the highest electric or the best electrical efficiency on that furnace based on design. Those three aspects will cover that.
Thank you. And Tenova, what's your comments on this further additions to this topic so far?
I think I'm in agreement with Gerhard and Simon. I have to say, we live in an industry, I call it first to be second. You know, whenever you want to develop a new technology, a customer always asks you, so where's your references? That's the world we live in. So I'm Simon's biggest fan at the moment to get the near smelt furnace working, because the industry, us as a technology industry, needs these references to work. And money can solve a lot of problems. Honestly, that's the reality we live in. The problem is the capital that is associated with solving these problems may put the flow sheet viability at risk. And that is a really difficult challenge to overcome. Yes, we're building 120 megawatt furnaces. The furnaces are expensive. We're producing an interim product in some instances. Sometimes, depending on touching on Gerhard's world map, you may have to, the only place it makes the most economic sense is where you produce granulated pig iron. The moment you produce granulated pig iron, you may need to do secondary metallurgy to fall into spec. So there's so many complexities in the flow sheet that Tenova's point of view is, and we want the reducing furnace technology to work, and we're voting for our competitors. We're really hoping that it will work. The bottom line is, if you end up doing an OPEX calc or a return on investment calc and you're borderline with what is today an unproven technology, and when I say unproven, I'm not talking about 6-line furnaces, I'm talking about using it for this specific application, it becomes a hard sell. And that's what I think everybody is facing. And that's why it's so great to hear Dr. Wimmer's approach on doing test work, what Simon's doing, what the guys at Metix have done, the test work that we've done. I think we've all corroborated each other's points of view on the process. So again, take the competition out of the equation. As metallurgists, we're moving in the right direction, and we're moving in the same direction. But it's going to take a lot of time for this technology to implement. And I think that's why the moments I had, our focus is a little bit more on, in addition to the primary technologies, I think we also need to look at the complementary technologies to the existing flow sheets to see if we can fast track some of the decarbonization needs that we will face, not in 15 or 20 years' time, but tomorrow or the day after tomorrow. Thank you.
Great. Thank you. That was a very important answer. I think important point you made, and I guess that's the general challenge that we're looking to try and help to de-risk from the HILT perspective, is because yes, things can be done, but the question is how we understand the broader question of, because it's not just the technology, it's the energy costs. All of these things are in supply chains, which are very important in understanding how to lower those costs and where these technologies move forwards first. So Simon, if we can maybe return to you to add a few more comments. Firstly, maybe if you could start by, you talked about 100 megawatts, but can you also maybe link that back to million tons per year or something in scale for our listeners? That might be a good starting point, but maybe you can pick a bit more about how you see the trajectory coming down, where the economics will likely stack up first, and how you see the technology gradually moving forwards.
Yeah, I mean, it's a fascinating conversation that we're all having here, and this is the great thing about discussions like this format that you've put together here, Gus. And just in terms of that capacity throughput, I mean that single DRI into 2 ESFs or 2 into 3 or whatever we end up looking at, all of that capacity is trying to align with something pragmatic to replace a typical modern blast furnace of, let's call it 3 to 4 million tons per annum. So they're the sort of numbers that we're always circling around. If we can't legitimately claim that we have line of sight to being able to do a blast furnace capacity replacement, I don't think we're talking the right language for long-term commercialization. So we've always maintained that we need to be injecting that into even the earliest conversations around, is this technology techno-economic, to Andre's point. I think he made some very good comments there. I guess also, I often reflect on, it's an interesting industry because you meet, I mean, even on the call today, we've got specialists from each one of the technology providers that have been in the industry for decades themselves. And I often find myself asking, what fundamentally keeps us all doing what we're doing? And that is, it's such a fascinating space from an engineering perspective. And one of the key points to that, from my perspective, is you can actually change the techno-economics of these pieces of equipment, particularly smelting furnaces, based on your operating modes. We've probably all seen cases where furnaces have been upgraded from submerged or partly submerged to open bath or semi-open smelting, and completely changed their capacities, throughput capabilities, techno-economics without any equipment updates or limited equipment updates. And so what we're really going to learn, I think, in some of these first implementations is not so much around how do you design the box, because like I said, we certainly have lots of references to give us confidence around the box being okay from an equipment perspective. It's more about the subtlety in how you feed, how you get the metallurgy to give you the carburization into hot metal that you need, how you handle the flow rates on the various metal and slag sides of the furnace. It's that integration and techno-economics at scale, which is going to be really critical. And that's why the actual scale of some of these next examples to be implemented are really important. Are they at the right size that then allows you to make that leap from something that can be, I guess people can get their heads around in terms of supporting from a development perspective, to that true commercial scale as the next implementation opportunity. So that's the challenge for the industry, and it's certainly exciting times.
Great. Thank you, Simon, and thank you all. So we're approaching the end, and we don't have a lot of time left, but what I'd like is to give each of our companies the chance to give maybe 1 minute only, but to give your perspective on how you see the pathway moving forwards towards commercial implementation for each of your respective platforms, where you see those critical steps in that pathway, and you can adapt something different from the previous one, but maybe back to Primetals. Gerhard first, please. Thank you.
So all this green transition will be costly. The blast furnace is unbeatable when it comes to cost, when we are not including the CO2 emissions. So the cost for CO2 emissions are there. We are all paying them. We have to address this cost to the emitter, and one of them is the blast furnace. So as long as politics does not manage that these costs are directly addressed to the blast furnace, all these new technologies we are discussing today will not have a chance. So this will be the first step. Second step, if this is the case, then these green technologies have a chance. The question is where to install them. Are the locations where we do iron steel making today, for example Europe, the right locations in future? Or might we shift the energy intensive step, the iron making step, to regions where green energy, green electricity is more easily available in future? These are the two questions I think that will be decisive, where and when this plant is going to be built.
Excellent points. Thank you. Gerhard, please.
Great, thank you. And I fully support Dr. Wimmer. I mean, from our side, it's the same. I mean, the OPEX and the CAPEX are our main drivers. And we do understand the impact that carbon tax, ETS, CBAM, etc. has on all these different OPEX calculations. So from our side, the way we see commercialization is regional specific, and specifically linked to what was said earlier on the whole issue of carbon taxation and ETS and all these other mechanisms. And then obviously where electricity is abundant and cheap, considering what has been installed already. So from our side, and I mean, most of the speakers, I mean, Simon also referred to that, technology is available. It is to put it in the right region and make sure that it stays profitable.
Thank you. Excellent points again. Tenova, one of you would like to take a presentation? Thank you.
Just a comment from my side. We have seen in Europe what happens if you go down the path with all the transformation, with all the risk and challenges. And in Europe, especially, the energy costs are extremely high with all the trends for artificial intelligence and data centers and so on and so forth. So demand is rising exponentially. And that's what most of the customers are facing, are the energy intensive, or the energy intensive industries are facing here, is these extreme costs and risks from the transfer to carbon-based to electrical-based transformation of the steel industry. And in my opinion, that's exactly Australia's strengths, the availability of green energy. And if you grow in that field, the industry will follow automatically. This is my view on the things. Thank you.
Thank you very much. And Simon, please.
Yeah, I think all of us have lived through at least one cycle now where governments around the world have got very excited about all this, only to realise the enormity and complexity of the task ahead of us and the cost. And some of that excitement has come off in obviously Europe and the US in particular. But I look to NeoSmelt for the hope from the industry side, where we've got, like I said, 5 industry participants in that joint venture. I mean, if that doesn't indicate the seriousness of it from an industry perspective and the value that they see in continuing to push for transition, nothing will. So I'm very encouraged by that. I didn't expect to see that in my career, having that sort of diversity of client groups come together to solve a problem together. And I think that speaks volumes to the motivation of the industry to keep pushing this forward. And I think ultimately that will get this across the line. So, like I said, exciting times ahead for all of us, and very, very pleased to hear the conversation today. I think this certainly helps.
Great. Well, on behalf of all of the audience here, and on the behalf of the HILT CRC, I'd like to thank all of our speakers for an outstanding set of presentations. You've really provided great insight and a lot of experience you brought to the table, and we really appreciate it all. So on behalf of everyone, I'd like to add my thanks, and I'm sure all of our online listeners will do the same. Thank you again.
Thank you.
Thank you, everyone. Have a fantastic day.
Thank you all. Cheers.
Thank you. Bye.
Thank you.
Bye.
Thanks to HILT.